question, and I've got my own opinions about it, and I know where I want to draw this, but we'll see where it goes. The question I want to ask is one that I first experienced when I was looking for a job after I got my degree. And I happened to be visiting a Department of Computer Science, and they were in the middle of the philosophical discussion, what is computer science? And so they turned to me and asked me what I thought. And so I've been thinking about it ever since. I don't remember what I said then. I don't remember what they said. But let me ask you, if someone were to ask you, what is computer science? How would you narrow in on an answer? And part of the way of answering that is to say, well, I would consider motorcycle building not computer science. All right, so we can perhaps say what isn't. And you might say, well, numerical methods, that is computer science, although you might not. So what is inside the boundary of computer science? And then we'll try to generalize what that really constitutes. Yeah?
I don't have an answer to what is computer science. I do have one thing I think is probably not computer science.
Okay.
That what I think it is, which I don't think learning to program is necessarily computer science. I think you can know programming and not program without being computer science.
Okay, so the ability to program, the skill of programming, is perhaps not computer science. Nonetheless, we teach it, and maybe we shouldn't, or maybe we need that for other things that we come to later.
I think you do need to know how to program in order to do most computer science, I would imagine.
Right. Like people would agree that physics is not electrical engineering, but you need a certain knowledge of electrons in order to do electrical engineering. So it's prerequisite to, but not part of. Okay, so that's something which is, programming is not computer science, fine. Yeah?
To just what is computer science?
Yeah.
So I think a good definition is probably applying the scientific method to complex problems using computer software and computer systems.
Okay, there's three parts then. Applying scientific method to problems involving using a computer to help you.
Yeah.
Okay, so the scientific method, people will disagree what that is, but according to, what's his name, Kuhn, the scientific method is having hypotheses and then designing experiments which can falsify the hypotheses, and then running the experiments to see if those hypotheses survive the falsification. I don't think we do very much of that. I don't have any hypotheses that I've tried to solve. So maybe that's computer science. And then the last part I think I might agree with, which is using a computer to help you do that. But then you look at someone, again, let's go back to physics, who uses enormous amounts of computer time to simulate quantum electrodynamics, QED, I guess it's called. And there is an underlying theory of interactions of quarks, and they have a hypothesis, and they use computers, but the result, the whole thing isn't really, to my mind, computer science. It's really physics. It's fundamental physics. So I think we can modify that definition perhaps to get to mine, but it's not close yet.
That's good.
Yeah. Yeah, Daniel.
Maybe learning to program isn't computer science, but programming languages definitely are. How you model, how you write a program.
Yeah, so the study of programming languages is. Learning how to program isn't. All right. So, yeah.
In terms of using a computer to help you solve scientific problems and math problems, I think I would consider Alan Turing's Bob machine to be computer science. Even though that was the first instance of using a computer to solve a math problem, right? Am I correct about that?
This is Alan Turing's
Problem?
well, there was Babbage's engines.
It was never built though.
Well, the design. And the difference engine wasn't built, the first one was.
It was never used to solve problems though.
But it could have been.
Okay.
In fact, it was programmed by Countess of Lovelace,
Yes.
Ada, even though the programs could never be executed.
Yeah. All right.
say yes,
Yeah,
but people could disagree.
I think I would also say yes too. I'm not entirely sure why.
Yeah, yeah. Yeah, what do we,
That's your descriptive phrase. I think computer science is the study of how one mechanizes mathematics.
that's a nice short definition. Computer science is how one mechanizes mathematics. Well, when I was a graduate student, one of the programs I used a lot was called Maxima. It still exists, although it turned into MATLAB at some point. And what it is automation, at least what Maxima was automation of what you learn in a college algebra course or beyond. It could do differentiation, it could do factoring, it could do all sorts of useful stuff that we had to learn how to do by hand. It was the mechanization of that mathematics. Now, one can mechanize other kinds of mathematics. I don't know about topology, for example. One can mechanize that. But certainly, a lot of the algorithms that one learns in order to do calculus are statable in such a way that you could mechanize them. On the other hand, is it mechanizing mathematics to do compiler construction? I would say that the study of compiler construction is in computer science, but I would say that it's not a mechanization of anything mathematical. Although you might disagree, you might say, well, parsing methods are mathematics. And you might say, denotational semantics is mathematics. And all the compiler does is it mechanizes that for you. Maybe you can make a point here. It's a reasonable point, yeah.
The question is harder because it's asked, what is computer science? But perhaps the question is easier if we are asking what we are doing is a science of. What is this thing that computer science is a science of?
What are we studying?
But there are natural sciences and things are clear there. We want to learn about the material universe. There are social sciences and things are clear there as well. We are studying human behavior and perhaps societal behavior. And I think that we cannot really answer the question, what is computer science, without really asking, what is it that we are studying? Is it material universe? If in the example that you had from physics, I think computer science provided tools. Perhaps these tools could be better framed within the term of computational science. So that it is a tool of doing science in a particular area. This is still physics. And earlier people would be using whatever devices they wanted to do some science with them. Now they are using also computers and computation. It is still physics. So it's not computer science, it's physics. So what are we studying? This is the key question.
Right, and now let me give you my answer to it. Because I've been thinking about this for 40 years. And so over time, I've kind of solidified what I think is a reasonable first approximation of an answer. I think the thing that we are studying is algorithms. And we are developing algorithms. We are developing facilities to execute those algorithms, such as programming languages. A programming language isn't an algorithm, but it's a facility that one needs in order to express an algorithm. What we just learned about phonics, those are algorithms that you've been describing. And the study is not, what one could say, oh, this is biology. What one can say, it's computer science to the extent that it is the study of algorithms that can be helpful in doing such things as clustering. There are clustering algorithms, and you've been developing clustering algorithms. There are big data algorithms, analysis of large amounts of data, finding outliers. There are algorithms for that, and what you've been describing is a particular set of algorithms. And insofar as you are studying the algorithms, I would say it's computer science. And so I think that calling what we do computer science is maybe a bad idea. Most inquiries that name themselves as science don't follow the scientific way of thinking. That is, biology does, but it doesn't say biological science usually, it says biology. And we don't say physical science, we say physics. When we say social science,
Maybe computers.
well, I'll get to what I would like to call it. Social science is not really a science in the sense that there aren't really experiments based on hypotheses. You don't want to do an experiment with a population of humans, all right? Well, I think we should call our study algorithmics. Just as we have statistics, mathematics, algorithmics. And I can even tell you what the abbreviation is. We say math and stats, right? Or in England, maths and stats. So this is ALEX, although it's a kind of ugly word.
As opposed to allergies.
As opposed to algae, yeah. Right. So algorithmics, and that leads me to the second half of my presentation. I would like to ask you, what do you think are the most important algorithms? Ranging from very simple, perhaps, things you learn in 315 or in 216, up to very modern stuff that people are using all the time, but you don't learn in elementary classes. So name one of your favorite algorithms. Yeah.
Just because it's a standard library, all of it.
Well, there's a standard library, all of it, but no, let's be more specific. Yeah.
Divide and conquer.
Divide and conquer. Now that's, to my mind, divide and conquer is a category of algorithms, not a particular algorithm. So let's name a particular divide and conquer algorithm.
There are many, but I can tell you that two algorithms that I would regard as extremely important are road sorting and hashing.
Okay. Now for sorting, there is a standard divide and conquer method of sorting. There are several. But what's your favorite divide and conquer sorting method?
I will say quicksort.
I would say quicksort too. Merge sort is also divide and conquer. And merge sort has a guaranteed n log n behavior. Quicksort has an expected n log n behavior, but it's actually a very good n log n. So let me wave my hands and show you how quicksort works before we get on to the next algorithm. How many of you have already know how quicksort works? Great, so I'll be able to review for some of you and describe for the other half. You've got this array of numbers and you want to sort them. We're going to divide it into subproblems. If it's short enough, we'll just do it. If it's longer than short enough, what we'll do is we'll pick any one of those numbers and hope that it's somewhere in the middle. We'll take all the numbers that are less than that and put them on this side, all the numbers that are bigger than that and put them on this side. That's called partitioning. It can be done in linear time. That is, if we have n numbers, in order and time, we can put the smaller ones over here and the bigger ones here, but they're not sorted within themselves. Smaller numbers, the number we picked, bigger numbers. And now, we've divided it, we conquer it by using the same algorithm on those numbers and on those numbers, recursively. Divide and conquer algorithms are recursive algorithms. That is quicksort, and all the rest is just details. All right, quicksort is the first great algorithm of the Western world. Right? Not only the Western world, it's a great algorithm. People should know it. People use it. Right. So, yeah, you have a suggestion.
For algorithms, pathfinding algorithms, the first one that comes to mind is Dijkstra, but I don't have it.
So shortest path algorithms in a graph.
Yeah.
So there are graph algorithms, and there is Dijkstra's shortest path algorithm, which is, it's actually all shortest paths algorithm, is it not?
No, it's one to all.
One to all, okay. And it's a breadth first search, am I right? Right. I don't remember it. It's been too long since I've taught 315. But, all right, so there's a graph algorithm example. And I expect people to use that one pretty heavily. Yeah.
So it's not an algorithm, but it's a question of bench for algorithms.
Yeah.
So I normally consider Unicode, the whole Unicode consortium, that idea to be part of computer science. It's very important to make sure all the
right, so the question is, are encodings of natural language letters like Unicode, are they computer science or not? They aren't algorithms in some sense, but they are encodings. And there are certainly encodings that I would say are algorithmic. For example, Huffman encoding, compression methods. Now Unicode is not itself a compression method, although there are compressed versions like UTF-8. But it's a standardization, if you will. There are standardizations that have appeared throughout the history of computer science. For example, how do you represent a floating point number? For a long time, there was no one standard, but now there is, the IEEE floating point standard. And it's nice to have a standard because then people can build algorithms that use that standard, right? Is building a standard representation computer science? I don't know, it's kind of near the border.
I would say that we have to distinguish between science, applied science, and professional computer science. And so there are these three aspects, and all of them are related. They are about something else. And to some point, I think, work on standards or things that become eventually a tool of a trade for a professional computer scientist. Up to a certain point, this is science, maybe sometimes applied science, maybe sometimes engineering as much as applied science. But at some point, it becomes not science, not a subject of science, not science, it's just a tool.
Just a tool, right. So building the tool, designing the tool, that was science. Once the tool is
Or
there.
applied science,
Yeah.
at the same level as engineering is applied physics.
Oh, well, let me tell you what I think engineering is. The one-word definition of engineering. Because I've given you a one-word definition of computer science. My one-word definition of engineering is 2 words. Problem solving. I think that's what's at the center. Now, you can have problems in building chemical plants. That's chemical engineering. You can have problems that you need to solve in building buildings. That's mechanical engineering, more or less. It's not all of mechanical engineering. And then there are problems having to do with, well, generating electricity. Okay, fine. That's so. Anyway, we are in the College of Engineering, and it fits pretty well because much of what our algorithms are intended to do is to solve problems. And part of what we do on an everyday basis is, when we're given a problem to solve, decide what algorithms we will use for it. Well, another algorithm that was mentioned was hashing, which was originally called scatter storage. How many of you already know what hashing is? Great, I won't talk about it. I won't use my hands to define it. But I use hashing every day. Yesterday, someone gave me an interesting problem to solve. And one of the various pieces that I put together to make it work involved hashing. It just worked out nicely that way. Hashing is so important that you find it in data structures in modern programming languages. You won't find it in C, but you will find it in Python, in Perl, in JavaScript. Built into the language, you find that in Java as part of the library, but it's built into the language in many languages now. It's so important. Now, someone who hasn't yet made a suggestion, another algorithm, please. Yeah.
I like the fast primality test.
Fast primality tests. When I was a graduate student, I took a course which is, here's some neat problems, see if you can solve them. And one of the problems was, in less than 10 seconds of computer time, computers were slower then. Now we'd say in less than a tenth of a second or less than a 100th of a second of computer time, find the highest pair of primes you can, a twin pair. A twin pair of primes is 2 numbers which differ by 2, which are both primes. For example, 11 and 13, that's a prime pair, right? And so how do you do that? And different people came up with different methods, but they needed to use primality testing, right? Because if you have a hypothesis, these 2 numbers are a twin pair, then you want to test, are they in fact prime? And now that's just a game. I'll tell you later how I solved it. Mine was the fastest in the class, but didn't get the highest twin pair in the class. Mine found the highest one within the range of normal integers, 32-bit integers, I think it was. Or maybe it was 16-bit integers. I don't remember what integers we had, 23-bit integers, whatever it was on the computer we had. But there were some people who got much higher by using other methods. Anyway, what do we use primality testing for mainly these days?
I want to say encryption, but
Yeah, cryptography.
Generating primes.
Yeah, for generating primes. And we need to generate primes in order to get keys for such things as the RSA encryption methods, public key encryption. And so generating primes, yes, and being able to tell quickly if a number is prime. The method I used for testing primality wasn't, the modern methods weren't known back then. And so what I used is the inverse of Fermat's little theorem, which says that if a number is prime, then certain things are true in group theory. And if those things are true, then, and you make enough tests, the number is most likely prime.
It's very, very effective.
Right, and so that's what I did, 3 or 4 tests. And if it passed those 3 or 4 tests, I said, it's prime. Even though I might have been wrong. Okay, primality testing is a great algorithm.
that is the one I was thinking of, the inverse Fermat's.
Oh, was, okay, because there are other methods these days. One can do in polynomial time, one can tell for certain if a number is prime. And I remember hearing a lecture about that Professor Clapper gave years ago. And I must say, I understood the first 5 minutes of a half-hour lecture. Yeah. Yeah.
I just wanted to connect it to the connection.
You may stand.
To the previous discussion. How many of you know how old is our department? Okay.
The integer is not a prime.
Okay. You don't know. Okay, it's one of the oldest in the nation, 50 years, and we will be celebrating with banquet next week. Unfortunately, I haven't seen many students signing up. I haven't seen some faculty sign up for the event either. So how does it connect to our discussion? Okay, when the department was being created, it was created by one of the members of the curriculum committee, who was the first chair of the ACM, who was the first chair of our department. And at that time, there was a very intense discussion on 2 topics. One, what is computer science? And the discussion, the committee, the curriculum committee, defined it. I don't remember the date because I wasn't prepared for this class. But it was about, I like your answer, but I like what Dr. Tushinsky said. I like your answer for all those reasons. I like algorithms. I will tell you what are my favorite, just to counter one of your statements. But okay, just it is about information. And everything what is related to information, like processing, storage, okay, using that information to produce results like from functions. That was a discussion. And the second item was that at that time, there was a statement, there was also a statement from Professor Navarro, the first chair of the department, that computer science may not be the most fortunate name for this. And the discussion is continuing. In 2005, if I remember, very recently, there were articles in the ACM, is computer science science? Such to others. So that's a very alive thing. But now, I would like you to join our celebrations next week. Talk to Ms. Diane, it will be really fantastic. I haven't seen you today, have you? Okay. Yeah. But now just, what is my favorite? Because Dr. Finkel said the biggest achievement of the Western culture is, or algorithmics, is quicksort. I would say my favorite are Russian peasant multiplication algorithm, because it's about Eastern culture. I'm not Russian, I'm Polish. Or sometimes called, the algorithm is called Japanese, so Asiatic. Okay. And Greek algorithm coming from Greek.
The Euclidean greatest common divisor algorithm.
It's not because I like it, I do, but it is just because it kind of set the stage.
Great. Well-
no matter what, this one is also fundamental for nowadays cryptography.
Right, right.
We cannot do without it.
One of my fellow graduate students had on his wall, on his blackboard, a list of his 20 favorite algorithms, the ones he thought were at that point the most important, and I'm sure Quickserve was there. I don't know if primality testing was, because the RSA algorithm hadn't been invented yet. Okay, well, stay tuned. We'll meet again next week to keep current. Thanks.
Thank you.